Hello, I'm Lorenzo, and I'm going to present this paper about wikis distinguisher for AES. I would like to start this presentation by introducing the concept of wikis and open key distinguishers. A key is said to be weak if it makes the cipher behave in some undesirable way, so if it makes the cipher weaker with respect to other keys. If the fraction of wikis is rather small, then wikis are not a problem in general for the security of the cipher. However, wikis could become a problem if the adversary has some control over what keys are used. Just to give an example, if a block cipher is used in a mode of operation intended to construct a secure hash function, for example using the Davis-Meyer construction, then obviously there is no secret key material, so the adversary either knows the key or it can even shows the key that instantiates the cipher. Now, if you want to analyze the security of a cipher in such a model, we can use open key distinguishers. So we have a non-key distinguisher for the case in which the attacker just knows the key, or chosen key distinguisher for the case in which the attacker can shows the key that instantiates the cipher. The goal of open key distinguisher is to find a property of the attack cipher that holds with a probability which is higher than for an ideal cipher. In this paper, we focus just on chosen key distinguisher, and we just focus on AES. As final result, we are going to present a 9-round chosen key distinguisher for AES 128 and a 12-round chosen key distinguisher for AES 256. Both distinguishers are based on the multiple of n property, which was proposed for the first time at Eurocrypt 2017, and both distinguishers work in the single key model. There are other chosen key distinguishers for AES in the literature. For example, we have a chosen key distinguisher for 8 round in the single key model and one on 9 round of AES 128 in the related key model, while for AES 256 we also have a chosen key distinguisher for full AES 256 in the related key model. We just remember that the related key model is simpler, is in some way simpler than the single key model because the attacker has more freedom. So the property is based on related keys, so the attacker potentially has more freedom. So in order to present this result in more details, the presentation is organized as following. First of all, we are going to introduce the concept of weak keys as space trace, which is basically something in the middle between an invariant subspace trace and a generic subspace trace. As next step, I'm going to recall AES, and I'm going to present weak keys for AES. Then, based on these weak keys, I present some weak key secret key distinguisher, which are obviously are based on this multiple of n property. And then, using this secret key distinguisher, we are going to present the chosen key distinguisher for 9-round AES 128 and 12-round AES 256. In this presentation, I just focus on AES 128. If you are interested on result on AES 192 or AES 256, you can have a look at the paper. So let's start with weak keys space trace. As I said, these weak keys space trace are something in the middle between subspace trace and invariant subspace trace. So I'm going first to record the definition of subspace trace and of invariant subspace trace. I try to explain why there is a gap between these two concepts, and then I'm going to fill this gap by introducing this concept of weak keys space trace. So in this presentation, but also in the paper, we just work with iterative cipher. So an iterative cipher is defined in this way. We have a key, and we use a key schedule to generate several subkeys, K0, K1, K2, Kr. And the encryption is defined in this way. We take the plaintext, we XOR the plaintext with the first subkey. This becomes the input of the first round, and then we repeat this step several times until we reach the final round. We take the output of the final round, we XOR this output with the final subkey, and we get define a ciphertext. In the following, I use the notation R to denote the round without the key addition, and the notation R with the subindex k to denote the round with the key addition. Now, subspace trays were introduced at FEC 2016, and it is the following. We have a collection of set of subspaces U0, U1, U2, US, such that the dimension of UI is smaller or equal than the dimension of UI plus 1. If this condition is satisfied, so if each coset of UI is mapped into a coset of UI plus 1, then we have a subspace tray of length S. And if the dimension of the subspace is constant, then we say that the subspace tray has constant dimension. So the crucial point here is that this property must hold for each coset of UI. So each coset of UI must be mapped into a coset of UI plus 1. And this is very, very important because if this is the case, then this condition is basically independent of the value of the key. So as you can see here, the key only changes the final coset, but the fact that this coset is mapped into a coset of this subspace just depends on the details of the round function. So for subspace tray, we don't have any condition on the key, but we require that each coset of UI is mapped into a coset of UI plus 1. Now, for invariant subspace tray, we have condition which is quite similar, obviously. As you can expect, the subspace is invariant. So as you can see, the subspace before the round function and after the round function is the same. However, we have an important difference. So we don't require that each coset of IS is mapped into a coset of IS, but the condition is the following. So first of all, we work with a set of weak keys, and for each key in this set, so for each weak key, we ask that there exists element A0, A1, A2, AES, such that the coset IS plus econ I is mapped into the coset IS plus econ I plus 1. So we don't require that each coset of IS is mapped into another coset of IS, but that some coset are mapping into other coset, and this coset also depends on the value of the key. So, as I just said, there is a crucial relation between the coset that satisfy this condition and the set of weak keys. For example, we have that the subkey ki must belong into this coset of IS, and I just would like to mention that this definition is a simplified definition because potentially we can replace this element A0, A1, A2, AES with a set econ I. So in one case we have a condition which is independent of the keys. In the other case we have a condition that depends on the key, and we also have a restriction on the subspace. So we can fill this gap by introducing weak key subspace tray. So we don't require anymore that the subspace is invariant, but at the same time we don't require anymore that each coset of econ I is mapped into a coset of econ I plus 1, but as in the case of invariant subspace, we just require that some coset of econ I are mapped into coset of econ I plus 1, and depending on the value of the key. So just to be a little more, bit more formal, we have again a set of weak keys. We have a collection of subspaces which don't have to be invariant, and we basically ask that for each weak key there exists element econ 0, econ 1, econ 2, econ S, such that the coset econ I plus econ I is mapped into the coset econ I plus 1 plus econ I plus 1. Just to highlight the difference between subspace tray and weak key subspace tray, let's have a look to what happens when we talk about truncated differential. Now, if we have a subspace tray U and V, So this basically we have that each coset of U is mapped into a coset of V, or equivalent, if we take two elements whose difference is in the subspace U, then after one round the difference of these two elements are in the subspace V with probability 1. But basically this means that one of the two input elements is completely free, so we don't have any condition on one of the two elements, and the other one, we just have one condition on the other element, and the condition is that this Y must belong in the coset of the subspace U defined via X. Now what happens when we have a weak key subspace trig? So again, let's say that U and V now is a weak key subspace trig with respect to the set of weak keys. Also in this case we have a probability that is very close to the previous one. We obviously have the condition on the key, so we need that the key is a weak key. But now the crucial point here is that we have a condition on both inputs. So we don't have a condition just on the difference, but we need that both inputs are in the coset of U that depends on this value, a k that depends on the weak key. So in a generic truncated differential, we just have one condition on the on one input elements, and we have or equivalent, we have a condition just on the difference between the two input elements. In the case of a weak key subspace trig, we have a condition on both inputs element. Okay, so now we have this concept of weak key subspace trig, so let's try to apply this concept on AES. So let's try to find some result using this new tool. Well, AES is a SPN block cipher which is based on a design principle known as white tree design strategy. The block size is of 16 bytes, which are organized in a 4x4 matrix. The key size can be of 16, 24, or 32 bytes, and depending on the key size, we have 10, 12, or 14 rounds. Each round is composed of 4 steps. We have the key addition, the S-box layer, the shift rows, and then the mixed column operation. Now, before talking about the invariant subspace trig of AES, I would like to briefly recall the subspace trig for AES. And in order to do this, we have to introduce some subspaces, which are the common space, the diagonal space, the inverse diagonal space, and the mixed space. So without going too much into the details, a diagonal space is a subspace of text with active diagonals and constant diagonals. We denote this set by the letter D, and this index, for example this index 0, denote the position of the active diagonal. It is not hard to prove that a coset of this diagonal space is mapped into a coset of a common space after one round, where in a common space we have active column and or constant column. After one more round, without the final mixed column operation, we have an inverse diagonal space, where basically it's a subspace of text with active anti-diagonal or constant anti-diagonal. And after one full round, the column space is mapped into a mixed space, which is just defined by applying the mixed column operation to the inverse diagonal space. So the collection of subspaces, which are the diagonal space, the column space, and the mixed space, is a subspace trig of AES of length 2, because each coset of the diagonal space is mapped into a coset of the mixed space after 2 rounds. So what about an invariant subspace for AES? Well, let's start with a keyless AES round. In this case, we can identify this subspace IS, which is defined as following. So the invariant subspace is composed of 2d64 texts, where basically the first column is equal to the fourth column, and where the second column is equal to the fourth column. It's not hard to prove that this subspace is invariant for Kira's AES round, in that the S-box works at byte level and the mixed column works at column level. So for sure this subspace is invariant for the S-box and for the mixed column operation. And if you apply the shift rows to this subspace, it's not hard to prove that we get the same subspace after this operation. So what happens when we consider the real AES round, so also with the key addition? Well, in this case, we have an invariant subspace for two rounds if the key is a weak key, which means that the key is in this subspace. So the subspace of weak keys is defined by the set of texts with equal columns. So the first column is equal to the second one, to the fourth one, and to the fourth one. If this is the case, it is possible to prove that the invariant subspace is mapped to the invariant subspace itself after one round, and after two rounds it is mapped into a coset of the invariant subspace. The crucial point here is that this result holds only in the case in which we start with the invariant subspace. So if we start with a generic coset of the invariant subspace, this result doesn't hold anymore. So we can get similar result, but at least we have to change the set of weak keys. Okay, so we have now an invariant subspace twig for two rounds AES. So let's try to exploit it in order to set up weak key secret key distinguishers. So in the paper we present several weak key secret key distinguisher. For this presentation, I limit myself to present the one based on the multiple of n property. So just to recall this property was proposed at Europe 2017, and the idea is the following. First of all, we consider a set of 2 to the 32 times t chosen plaintext with t active diagonals. So basically this corresponds to a coset of a diagonal space. And the idea is to count the number of different pairs of ciphertext after 5 rounds of AES without the final mixed column operation for simplicity, which are equal in a fixed anti-diagonal. Or, if you want, the number of pairs of ciphertext which are in the same coset of an inverse diagonal space. So it is possible to prove that this number is always a multiple of 8, independently of the secret key, of the details of the S-box, and of the mixed column matrix. Now, what happens when we use weak keys? So, what happens in the case in which the key is a weak key? So, in this case, let's consider to the 64 chosen plaintext in the invariant subspace AES that we just defined. And in this case, we are going to count the number of different pairs of ciphertext which are equal in x fixed byte. So we don't limit ourselves to consider anti-diagonals, but we just consider a pair of ciphertexts which are equal in a certain number of bytes. For example, in this case, we consider the number of pairs of ciphertexts which are equal in the first byte, in the byte in this position, and so on. So again, we can translate this probability using subspace. So we are basically counting the number of different pairs of ciphertexts that belong into the same coset of a particular subspace X that depends on the position of this 0 byte. A formal definition of this subspace X is given in the paper. I just omit it in this presentation for simplicity. Now, if you consider this number, we can prove that this number is always a multiple of 2 with probability 1, independently of the details of the S-box and of the mixed column matrix. Just to have an idea of the proof, as you can expect, the proof is very similar to the one proposed at Europe 2017, and it is basically based on the mixed differential property that we proposed at 2019. So the idea is the following. We have 5 rounds of AES. For simplicity, we just omit the final mixed column operation. And we know that if we start with the invariant subspace, and if the key is a weak key, then this subspace is mapped into a coset of the same subspace after 2 rounds with probability 1. We also have a probability 1 property on the last round. So a coset of a subspace X is mapped into a coset of this subspace, which is basically obtained by applying the shift operation to the subspace X itself. So the first 2 rounds and the last round have probability 1, so this means that we can just focus on the 2 middle rounds. And in order to prove this property, our goal is the following. For each pair of texts S and T in this coset, we want to prove that there are other pair of texts S prime and T prime, again in this coset, such that this equivalence is satisfied. So if this equivalence is satisfied, then the property follows immediately, and the reason is that if this difference, for example, belongs into this space, and if this equality is satisfied, then also this difference belongs into this subspace. And so at the end, we have the multiple of 2 property. So to reach this goal, let's just introduce this notation. If we have a text in a coset of a subspace IS, then we know that this text depends on 8 variables, and these 8 variables are so 8 variables where basically the first column is equal to the third column and the second column is equal to the fourth column. For the follow-up, I'm going to recollect these variables in this way. So I first take the 4 variables in the first diagonal, and then I take the variable in the second diagonal. The reason is the following. So let S and T to text defined as before. The other pair of texts S prime and T prime that satisfy this equality are basically defined in this way. First, by mixing the set of different generating variables of S and T. So for example, if this set of four variables is different from this set of four variables, then we can just mix the set of this set of variables, and we get S prime defined in this way and T prime defined in this way, and we can prove that this equivalence is satisfied. So in this case, we have a total of 2 different combinations. In the case in which one set of variables of S is equal to the other set of variables, the corresponding set of variables of T, we can just replace such set of variables with random values. So for example, in this case, we just replace the first set of variables of S and T with random values. And in this case, the total number of different combinations that we can get is a multiple of 2. So at the end, we can prove this multiple of 2 property for 5 rounds of AES in the case of a wiki. We also have other properties. In particular, if we have again these 2d64 chosen plaintext in the bias space IS, and if we are going to count the number of different pair of ciphertexts which are equal in A fixed anti-diagonals, then we can prove that this number is a multiple of 128 for 5 round AES 128, and is a multiple of 2 for 6 round AES 128, with probability 1, again independent of the details of the S-box and of the mixed column matrix. So we have now a multiple of n property for 6 round of AES, and the multiple of n property for 5 round is a bit stronger. Okay, so now we have this multiple of n property, so let's try to use it to set up a new chosen key distinguisher for AES. I just recall that the goal of an open key distinguisher is to distinguish between a block cipher and an ideal cipher in the case in which the key is chosen by generating plaintext ciphertext pair which exhibit array property. So we are not going to give a formal definition of chosen key distinguisher, but we set up it in the following way. First of all, we describe the property that these plaintext ciphertext pairs must satisfy, then we show that we can efficiently construct such set of text in the case in which the key that instantiates the cipher is chosen by the attacker. And here the idea is to use an inside-out approach. And finally, we are going to prove, we try to prove, so we are going to show that it is in general hard to generate such set of text that exhibit such property in the case of an ideal cipher. So as you can expect, this property, the property that we want to exploit, is the multiple of n property, and it is the following. So the goal of our single key distinguisher, single key chosen key distinguisher, is to find a set of 2 to the 64 plaintext ciphertext pairs that satisfy the following properties. So let's start with the first one. We denote by 0, 1 to 15 the position of the byte, and we ask that for each subset I of this set, the number of different pair of plaintext that are equal in the byte in this position is a multiple of 2. We ask a similar property for the ciphertext sum. So again, let J be a subset of 0, 1 to 15, and we ask that the number of different pair of ciphertext sum that are equal in the bytes in position J is a multiple of 2. In the case in which the byte are form a diagonal or an anti-diagonal, we can ask a stronger property. So in particular, for each subset I of 0, 1 to 3, we ask that the number of different pair of plaintext that belong in the same coset of a diagonal subspace, where again this index I denotes the position of the active diagonal, is a multiple of 128. And in a similar way, we ask that the number of different pair of ciphertext that belong in the same coset of an inverse diagonal space is a multiple of 128. So using all these properties, we can set up a chosen key distinguisher for 9-round AES 128 and 12-round AES 256. And the set of weak keys is composed of 2 to the 32 keys. So let's show that we can construct this set in an efficient way for AES 128. The idea is very simple. We just consider 2 to the 64 text in the invariant subspace AES, and we choose the subkey K4 to be into the set of weak keys that we defined before. We define the plaintext as the 4-round decryption of this text T, and the ciphertext as the 5-round encryption of this text T. By using the previous result, it's quite easy to prove that the multiple of n property holds both on the plaintext and on the ciphertext. The idea is the following. As we have seen before, the invariant subspace AES is mapped into a coset of the invariant subspace AES after 2 rounds with probability 1, and after 5 rounds we have the multiple of n property in the forward direction. In the backward direction, it is possible to prove that the subspace AES is mapped into a coset of the subspace AES after 1 round decryption with probability 1, and so we get we can prove that we have the multiple of n property after 4-round decryption. What happens in the case of an ideal cipher? Well, we have to show that it is very hard to construct this set of plaintext ciphertext pairs in an efficient way. So if we just take 2 to the 64 random plaintext ciphertext pairs, the probability that the multiple of n properties are satisfied is very small. It's approximately 2 to the power of minus 100,000. And the reason is the following. So regarding the multiple of 2 property, we have approximately 2 to the 16 possible combination of byte where we can ask where we can impose a zero difference, and for each one of these combinations, the multiple of 2 property must hold. Remember that the multiple of 2 property holds with probability 1 half. For the multiple of 128 property, we have 14 possible combinations of diagonals or anti-diagonals, and again, this multiple of 128 property holds with probability 1 over 128, and finally this exponent 2 is due to the fact that the property must hold both on the plaintext and on the ciphertext. Well, potentially we can increase the number of pairs, and in that this is the case. So if we just use 2 to the 64 plus 2 to the 13 different plaintext ciphertext pairs, the attacker has a very good probability to find a subset of 2 to the 64 pair of texts that satisfy the required properties. However, the attacker must construct all possible subset of 2 to the 64 texts in order to identify the right one with high probability. And as you can see, the number of subset is approximately to the power of 100,000. So you can see that okay, the number of pairs is not too high with respect to the case of AES. However, the cost to identify the right subset of 2 to the 64 pairs is huge. In the paper, we also evaluated other strategies, and at the end, we conjectured that there is no efficient strategy to fulfill the required multiple of n properties in the case of an ideal cipher. As last thing, we would like to propose some open problems for future work. So in this presentation, in our paper, we propose several weak keys secret key distinguisher. So we have some open problems here. The first one is about the possibility to set up a weak key secret key distinguisher for 7th round AES 128, and the second one regards the possibility to exploit such distinguishers to set up an efficient key recovery attacks. Apart from secret key distinguisher, we also propose a new chosen key distinguisher in the single key model. And here we can identify two possible open problems. The first one regards the possibility to set up a chosen key distinguisher for full AES 128 or and AES 256, again in the single key model. And the second open problem, which regards the possibility to exploit such distinguisher in order to attack for example, an hash function which is based on the Davis-Meyer construction and that use AES as a cipher. So that's all. Thanks for your attention.